Okay, now let's talk about using some of these properties. These two problems here are just to practice the properties that I just covered. You can actually write this as a combination of logs. First thing I got to do though before I even start is I need to rewrite the square root of z as z to the 1/2 power. So let's write it like this to start out with. Now, there's a property up here that says the log of m divided by n. So let's say m is the numerator and n is the denominator, is equal to the log of m minus the log of n. So I can rewrite this as the log of the numerator, base 3, minus the log of the denominator, base 3. Well, then there's a property that says the log of m times n can be written as the log of m plus the log of n. So I can write the log of x squared times y cubed as the log of x squared base 3 plus the log of y cubed base 3. Now notice I put an extra set of braces around this next one here because I have this minus sign and I've got to write this. I'm going to write this as two terms. So I have the log of w times z to the 1/2, and using that product rule I can write that as the log of w base 3 plus the log of z to the 1/2 base 3. And these extra set of braces here are just to make sure I distribute the minus. So now I can also use the power rule here. The log of x to a power is the power times the log. So the log of x squared base 3 can be written as 2 log of x base 3. And same for the log of y cubed base 3 can be written as 3 log y base 3. And of course log of w base 3 is just log of w. Notice you've got the minus that goes with it. And then the minus also has to distribute through this term. So I have the minus here as well. But then log of z to the 1/2 base 3 using the power rule would be 1/2 log of z base 3. And so that's how you can use log properties to rewrite a single log as a combination of log. I can also use the properties to go the other direction and write a combination of logs as a single log. So for instance, if I have a number times log x, now here I didn't put a base, so we understand the base of each of these to be base 10. So if I want 1/3 log of x, I can actually move the 1/3 up here as a power and write that as log of x to the 1/3. And do the same thing with 2 log of y, and I can write that as log of y squared. And then 3 log of x can be written as log of z cubed. Okay, now let me show you here. This is a sum, so what I could do is I could actually write those as the log of a product, the log of x to the 1/3 times y squared. Okay, so those two would combine to give this. But then I would have minus the log of this. Well, remember that the difference of two logs can be written as the log of a quotient. So if I take this log minus this log here, then I can write that as the log of this numerator, x to the 1/3 y squared, over this denominator, z cubed. So that way I can write it as a single log like that. So you can go both ways. Let's talk about solving some exponential equations. You can use logs to solve exponential equations, and in most cases it doesn't really matter whether you use the common log or the natural log to do this, but you want to use one or the other because that's what you have on your calculator, is either the common log or the natural log key. So if I have 8 to the x plus 3 equals 500, if I were to take the log of both sides, I remember one of the properties said if m equals n, then the log of m must equal the log of n. Now, how does that help me? Well, the log of 8 to the x plus 3 can be written as the quantity x plus 3 times the log of 8. That's the power rule. And then over here I just bring down a log of 500. And now if I wanted to, I could go ahead and divide both sides by log of 8 so that I could get x plus 3 by itself. And then to get x, I just subtract 3 from this expression, log of 500 divided by log of 8. So just do log of 500 divided by log of 8 minus 3 to get your answer, minus 0.011. I usually just go out to 3 decimals on these. This one's a bit tricky because you're actually going to take the log of both sides here, but on both sides you have an exponent. I mean a variable exponent. So I'm going to use natural log this time. I could use common log, either one is fine. I'm going to use natural log this time. So I'm going to take the natural log of both sides this time. Well, the natural log of, now before I do anything here, let me make one little correction here. That should be a +1 right there. Okay, so if I take the natural log of 2x plus 1, yeah, if I take the natural log of 2x, 3 to the 2x plus 1, then I'm going to get, and again it should be there too. Okay, so the natural log of 3 to the 2x plus 1 would actually be 2x plus 1 times the natural log of 3. And then if I take the natural log of 7 to the x plus 2, that's going to give me x plus 2 times the natural log of 7. Okay, now what I've got to do here is I need to distribute the natural log of 3 through these two terms. Well, natural log of 3 times 2x is 2x times natural log of 3, but I'd prefer to write it with the x at the far right. So I'm going to write 2 times the natural log of 3 times x. And then 1 times the natural log of 3 is just natural log of 3. And then here I'm going to say x times the natural log of 7 is just natural log of 7 times x. And then 2 times the natural log of 7 is 2 natural log of 7. Now the reason I did all of that was because what I want to do is I want to look for these two terms that have the x in them, because I want these two terms to be on the same side of the equal sign. So I can take this natural log of 7 times x and move it to the left, and it becomes minus. And then since this natural log of 3 doesn't have an x in it, I can move it to the other side and it becomes minus. So I have 2 natural log of 3 minus natural log of 3 on the right. Then that allows me to factor the x out of here. And when I factor the x out of here, I get 2 natural log of 3 minus natural log of 7 equal 2 natural log of 7 minus natural log of 3. And then, now don't let this scare you, 2 natural log of 3 minus natural log of 7 is just a number. So to isolate x, just divide this number into the right hand side and then plug this in the calculator to get your answer. Now when you plug it in the calculator, make sure you put the numerator and the denominator in parentheses, and you should get 11.114. Now let's do a couple more. This one, the first thing I want to do first is divide both sides by 10 so I can isolate the log expression. So divide by 10, and then 500 divided by 10 is 50, and then this divided by 10 just cancels the 10. Now 0.06 over 12 actually is a terminating decimal. It's 0.005. So I am going to take the log of both sides here, but as I do so, I'm going to write this as 0.005. So I'm going to take the natural log of 1 plus 0.005 to the x equals natural log of 50. And then the natural log of this to the x can be written as x times the natural log of the 1 plus 0.005, which actually is just 1.005. And then to solve for x, I just divide the natural log of 1.005 into both sides, and then I get x equals the natural log of 50 divided by the natural log of 1.005, which gives me 784.35. And then this last one here, this one's actually much easier if you use the natural log, because this base is base e. And actually the natural log of e to a power is just the power. And that's using one of those power properties. So the natural log of e to a power is just the power. So that's just going to give me 5x minus 2. So when I take the natural log of both sides, over here I get natural log of 25, but when I take the natural log of this, I just get 5x minus 2. And then to finish solving this, just add 2 to both sides and divide by 5 to get your final answer. Okay, and now I want to end with a couple of log equations to solve. There's a couple of forms log equations can come in. If you take this log equation, on the left you can write this as a single log using that quotient rule. So the log of 2x minus the log of x minus 3 can be written as the log of 2x over x minus 3. And now this log, this is a base 10 log, right? So it's understood to have a base 10. So I could write this in exponential form and say, well, then 10 to the 1, which is 10, must equal this argument, 2x over x minus 3. And then now you just have a basic equation to solve for. The log's gone. So just multiply both sides by x minus 3, and you get 2x equals 10 times x minus 3. And I think you can solve it from there. That's just going to be 10x minus 30. And then subtract 2x from this side, add 30 to this side, and you get 8x equals 30. Then divide by 8 and reduce the fraction, and you get 15/4. The other thing you might run into, here we had a log equal to a number, okay? That's when you generally rewrite it in exponential form. But if you have two logs, like here on the right-hand side, I can use the log property that says the sum of two logs is the log of their product, and I can rewrite this as the log of 2z plus 2 times z minus 2, which would be the log, if you FOIL that, 2z squared minus 2z minus 4. So now I have a log on the left equal to the log of the same base on the right. So now I can just eliminate the two logs, because remember, the log of m equals log of n, then m, if the log of m equals log of n, then m must equal n. Okay, so now this, if I subtract 8 and subtract 3z from both sides, I get a quadratic equation, 2z squared minus 5z minus 12 equals 0. Then I can factor that and then set the factors equal to 0 and solve it, and I get z equal negative 3/2 and z equal 4. But the problem, we run into a little bit of a problem here. Here, z can't be negative 3/2, because if it is, it's going to make one of these logs, at least one of these logs, is going to have a negative argument. And remember, your domain for your logs has to be positive numbers. So throw away the negative 3/2. The only answer is z equal 4. Now this one's a little tricky, but let me show you this. The log of x cubed can be written as 3 times the log of x. But the log of x quantity squared, and that's not the same thing. See, the 2's on the outside. That's the same as log of x times log of x. Okay, so I just wanted to show you that. So now if I move this over to the left, if I move log of x quantity squared to the left, I get 3 log of x minus log of x quantity squared. Now, since both of these have a factor of log x in them, I can factor the log x out, and I get 3 for the first term, and then minus log x for the second term. Well, then for this product to be 0, either log of x has got to be 0, or 3 minus log of x has to be 0. Okay, so let's deal with log of x equals 0. Well, the only way log of x can be 0, remember this is base 10. So let's write this back in exponential form. So 10 to the 0 would have to equal x. But what is 10 to the 0? That's 1. All right, how about this one? For this to be true, log of x has to equal 3. Well, remember there's a 10 right here. So 10 to the third would have to equal x. And what's 10 to the third? It's 1,000. Okay. Now this one is actually much easier than it looks. See, this is 10 raised to a log of something with the same base, because this common log is base 10. And remember, if you have a base raised to a log of the same base, the base and the log cancel out, and you just get this argument here, 2a minus 7. So we just get, I used x here, but so you have 2a minus 7 equals 8. So a or x, whatever variable you want to use, is 15/2 for the final answer. And that's pretty much it on the algebra of exponential and log functions. And now, next we're going to get into the actual calculus of exponential and log functions.